Welcome to this explainer. Today, we're going to pull back the curtain on those chatbots that have seemingly taken over our world overnight. I mean, if you've been on the internet lately, you've definitely interacted with them, or at least heard people talking about them. Maybe you've used one to draft an awkward email to your boss, or asked it to plan a wildly specific 5-day vacation to Rome, complete with restaurant recommendations. You type a quick prompt and boom, a machine fires back a flawless essay, a poem, or a complex piece of code in literally seconds. It feels like absolute magic. But to truly grasp what's going on here, we have to look past that slick, user-friendly interface and understand the actual nuts and bolts that make this digital magic trick possible.
So let's dive into the central question you've probably asked yourself when chatting with one of these shockingly human-sounding AI programs. What is actually happening behind the screen? When it answers your questions with such perfect grammar and nuance, is it thinking? Is it reasoning the way you and I do? Or is it doing something else entirely? Well, it's really easy for us as human beings to project our own intelligence onto anything that speaks our language well. We're pretty much wired to assume that coherent speech equals a conscious mind. But to understand how a machine actually talks to us, and whether this illusion of intelligence is real, we need to look at a pretty fierce debate that's currently raging among AI researchers.
While some proponents argue that these tools are showing early sparks of genuine reasoning and artificial general intelligence, skeptics push back hard. They describe these models as doing nothing more than simply remixing and recombining existing writing. And this really highlights a massive foundational debate about machine intelligence right now. Are we talking to a genuinely new kind of alien mind that understands the world? Or are we just interacting with a really sophisticated illusion that mimics understanding perfectly? Well, to figure out who's right, we first need to strip away all the sci-fi hype and understand the underlying mechanics.
Let's start with Section 1. What exactly is an LLM?
Let's look at what these systems are actually built to do, from the ground up. Here's the definition, in plain English. A large language model, or LLM, is essentially a giant web of mathematical connections. It's a deep neural network that has read billions of pages of internet text. And why did it read all that? Just to get incredibly good at one very specific task, playing the world's most advanced game of autocomplete. Think about the autocomplete feature on your smartphone. When you text a friend and type, "I am on my," your phone probably suggests the word way. Now, it doesn't actually know you're traveling, it just knows that mathematically, way is the most common next word. An LLM is doing exactly that, but on a massive, totally unprecedented scale. It is not fundamentally designed to fact-check, or to calculate complex physics, or to hold true knowledge. It is simply designed to estimate the statistical probability of a word or a sequence of words popping up next.
That brings us to Section 2, the secret mechanic.
You see, how a machine processes language isn't the way you or I do at all. When we read, we see full words and sentences, and we instantly attach complex emotional and semantic meaning to them. The machine? It sees something completely different. Machines don't read whole words out of a dictionary. They read atomic chunks of text called tokens. A token could be a whole word for sure, but it can also be a piece of a word or even just a single character. For example, a word like unwatched is actually processed as 3 separate puzzle pieces: on, watch, and ed. By breaking text down into these bite-sized tokens, the model can compress data way more efficiently and recognize really complex mathematical relationships across a massive vocabulary. But for our purposes, just think of tokens as the fundamental puzzle pieces of language that the machine uses to do its math.
So the absolutely crucial point here is how it uses those puzzle pieces. When you give the LLM a prompt like, "When I hear rain on my roof, I blank in my kitchen," it calculates the statistical probability of how to fill in that blank. And what makes modern models so remarkably effective is that they evaluate the entire context at once. The model looks at every single word in your prompt to shape its prediction. If that prompt ended with the word bedroom instead of kitchen, the outcome would change completely. It'd probably predict a word like sleep or read. Because the model factors in the word kitchen, it narrows down its mathematical probabilities to things related to cooking or food.
And this brilliantly illustrates the math behind the magic trick. The neural network evaluates that entire context at once and generates a probability table. It calculates that cook soup has a 9.4% probability, warm up a kettle is at 5.2%, and cower is at 3.6%. Then the model simply outputs the token sequence with the highest probability, or it might occasionally select from the other top choices just to sound a bit more natural and varied. Keep in mind, it doesn't actually know what rain feels like, or what hot soup tastes like on a cold, dreary day. It just knows that based on the billions of human documents it's analyzed, those specific puzzle pieces frequently follow that exact context. But how does the machine get this underlying probability table in the first place? How does it actually know that cooked soup is the most likely answer?
Let's look at Section 3, Training versus Using.
Building these colossal models happens in two main phases. First up, the model undergoes massive pre-training. During this phase, it is fed an almost incomprehensible amount of text. We're talking about a massive chunk of the entire public internet, books, articles, websites, the whole shebang. It reads constantly, adjusting its billions of internal connections just to learn the basic, fundamental patterns of human language. It's learning grammar, sentence structure, and general facts purely by absorbing how words are repeatedly arranged. But a raw model that just predicts the next word isn't actually very useful for us. It might just ramble on endlessly, so it moves to phase 2, fine-tuning. Human operators train the model on specific structured datasets, often formatted as back-and-forth dialogue. This essentially conditions the model to behave like a helpful, polite conversational assistant that answers questions directly, rather than just continuing a thought into infinity.
Now for Section 4, a chatbot in action.
Let's put this all together and see exactly what happens mechanically when you ask a chatbot a direct question. And honestly, this is going to help strip away the illusion that there's some incredibly fast little librarian living inside your computer, sprinting to the back room to fetch facts for you. If you type the prompt, "Have the San Jose Sharks won the Stanley Cup?" into a fine-tuned model, it doesn't search a mental database of hockey knowledge, it doesn't query a sports encyclopedia, and it certainly doesn't try to remember past NHL seasons. Why? Because natively, it doesn't actually know anything in the human sense. It just sees a sequence of tokens. So instead of looking up a fact, it follows strict mechanical steps. Step 1, it breaks your hockey question down into tokens. Step 2, it runs a massive statistical equation through its neural network, utilizing its billions of parameters to evaluate the entire context of your prompt against everything it learned during that massive pre-training phase. And step 3, it predicts that the most mathematically likely next word to follow that specific sequence of text is no. It gets the answer perfectly right, not through comprehension, but through incredibly advanced pattern recognition. But because it relies entirely on these statistical probabilities rather than actual true facts, we run into a major limitation.
And that brings us to Section 5, the reality check.
This is where the magic trick occasionally fails, and the reality of the math is totally exposed. Sometimes, the highest probability tokens create a sentence that sounds incredibly confident and grammatically perfect, but is actually a complete and utter fabrication. Researchers call this a hallucination. For example, a lawyer might ask a chatbot for previous court cases to support a legal argument. The chatbot will happily invent an entirely fake court case, complete with realistic-sounding judge names, precedent numbers, and exact dates. Because the model is just guessing the next most likely token based on its training, it will confidently string together a highly probable sequence of words that is factually completely wrong. It doesn't have an internal truthometer. It has no mechanism to distinguish a real historical event from a fictional one. It only measures statistical likelihood.
And this is exactly why many experts refer to LLMs as stochastic parrots. Now, the word stochastic just refers to a random probability distribution, and a parrot, as we know, simply repeats sounds it hears without actually understanding them. According to skeptics, these models are just matching patterns and repeating highly probable sequences without any sentient understanding of what they are actually saying. Even when they solve a complex coding problem, summarize a lengthy news article, or write a beautiful poem, they are just relying on the statistical weight of the tokens they were trained on. It is a brilliant, breathtaking mimicking of intelligence, but it is not true comprehension.
So, it's a fascinating illusion to unpack, isn't it? And it leaves us with a rather profound mystery. If predicting the next word can mimic human intelligence this incredibly well, it really forces us to rethink what understanding truly is. It makes you wonder, how much of our own daily conversation is just an advanced form of autocomplete? These models might ultimately just be massive calculators playing the odds with puzzle pieces of text, but their unprecedented ability to generate language has absolutely changed our world forever. Thank you so much for joining me on this explainer. I really hope that the next time you use a chatbot to plan a trip or write an email, you'll be able to see the fascinating math behind the magic.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.